Okay, so this is chapter 13, Newton's laws of gravity. Okay, let's get started. Newton proposed that every object in the universe attracts every other object with a force that is directly proportional to the product of the masses involved and inversely proportional to the square of the distance between the masses. So we can write this law as follows. Let's consider two objects of masses m1 and m2 separated by a distance r between them, or by just a distance r. According to Newton, these two masses will attract each other by a force that is 1 proportional to the product of the two masses and 2 inversely proportional to the square of the distance between them. We can write this quantitatively as follows. So we have the force F. So we can write this as follows. Let's start off by first showing the two masses. Let's call this mass m1 and this mass m2. By Newton's third law, we can say the force of mass 2 on mass 1 is this force, and the force of mass 1 on 2 is given by that. The distance between the masses is this distance r. So according to Newton's law of gravitation, the force of mass 2 on mass 1 is equal to the force of mass 1 on mass 2, and that's equal to a certain force F, which we call the gravitational force, and this force is proportional to the product of the masses m1, m2, and inversely proportional to the squared distance apart. We can take out the proportional sign and include now a constant, which we shall call the universal gravitational constant. So we shall say F is equal to G times m1, m2 divided by r squared, where G is called the universal gravitational constant. This is an empirical constant that was measured by Cavendish in 1798. Its magnitude is below. So the magnitude of G is given by 6.67 times 10 to negative 11 newtons meters squared per kilogram squared. This tells us that if we have two 1 kilogram masses that are separated by a distance of 1 meter, then the gravitational force between them will be given by 6.67 times 10 to negative 11 newtons in magnitude. So this is just this is what the gravitational constant means. So let's write this in unit vector notation as follows. So we can write the gravitational force of mass 1 on mass 2, which is given by the force of 1 on 2 is this force here. It's equal to G m1 m2 over r squared times a unit normal vector r hat 1, 2, where if you drew this again, what this means then is that the distance between them again is r. This is mass 1, this is mass 2. So here are the forces involved. This is the force of 1 on 2, and this is the force of 2 on 1. And the unit normal vectors are vectors that point this way. So this will be r hat 1, 2, and this is the unit normal vector r hat 2, 1, like that. So you can see then that we need to put a negative sign here because of the unit normal vector, the way it's pulling or it's pointing. So the force of mass 1 on mass 2 is F12, and it's equal to minus G m1 m2 over r squared times unit normal vector r hat 1, 2. This tells us that the force of 1 on 2 is an attractive force pulling 2 towards 1. In this way of expressing Newton's law of gravitation quantitatively, we will also see that the gravitational force exerted by a finite-sized spherically symmetric mass distribution on a particle outside of that mass distribution is the same as if the entire mass of the distribution were concentrated at the center of the first mass. So suppose we have an object on the surface of the Earth like that. Let's say this is the mass of the object and this is the mass of the Earth. And we know that the force of the Earth on the object is that force, and in return, of course, the object pulls on the Earth that way. These two forces are action-reaction pairs. So by using Newton's law of gravitation, the force of the Earth on the object is equal to the force of the object on the Earth, and this is equal to the gravitational constant, mass of Earth, mass of object, over the radius of the Earth squared, where the radius of the Earth, of course, goes from the center to the surface of the Earth like that. So this is just an explanation of Newton's law of gravitation, which tells us that we can think of the Earth's mass as being concentrated at the center of the Earth and the object's mass as being concentrated at its center, so that we can think of the gravitational force between them as if the force were between their two centers. So in vector notation, we say that the gravitational force between two objects, let's say objects 1 and 2, can be written the following way. So we can say that the force of 1 on 2 is equal to minus g, mass of 1, mass of 2, divided by r squared, and then we have r1, 2 at. So this is the vector notation for writing that, and we can say that the force of object 2 on 1 is equal to minus the force of 1 on 2, that way. So we can say that the two forces are equal in magnitude but opposite in direction. We can also see that this way of writing Newton's law of gravitation tells us that this force is an inverse square law force. It falls off as 1 over r squared. So for example, if we were to plot the graph of the gravitational force against the distance of separation between two objects, we can write F gravitational like that on the y-axis, and we can write separation distance on the x-axis this way. And let's say, because we know this force is an inverse square law, it goes off as 1 over r squared, so we'll draw a force that goes like that. So suppose that this force is the initial force at a certain distance, 1r. If the distance is doubled between the two objects to 2r, the force decreases by a factor of 4. So this is F over 4. If the distance between the objects is tripled to 3r, we can see that the force goes off as F over 9. So the force decreases by a factor of 9. So this is an inverse squared law relationship. And the opposite will happen. Suppose you cut the separation between the objects in half, the force increases by a factor of 4. If you were to cut the separation between the objects by a third, the force will increase by a factor of 9, and so on. Let's look at examples of finding the gravitational force between objects. We shall start off with 2 objects first, and then look at the gravitational force between 3 objects. So let's call it case 1, force between 2 masses. So let's have 2 masses, mass m1 equals 100 kilograms, and mass m2 equals 200 kilograms. And let's take the distance between them to be 10 centimeters. We can draw a quick diagram for these 2 objects. Let's call it m1 and m2. The distance between them, notice that I've been drawing the distance to be from center to center, because as I mentioned earlier, the masses, or the force law, the gravitational force law, acts as if the masses are concentrated at the center of the object. So when I draw the diagram, I draw the separation from center to center. So here is the force of 2 on 1. Here is the force of 1 on 2. And these 2 forces just give you the gravitational force, which is given by this formula. So in this scenario, we just plug the numbers in and do the calculation. So here you have 6.67 times 10 to the negative 11 multiplied by 100 kilograms multiplied by 200 kilograms, and you divide that by 10 centimeters, which is 0.1 meters squared, like that. And you can do the calculation to find the answer. So what we have then will be 6.67 times 10 to negative 11 times 1 times 10 to 2 times 2 times 10 to the power 2 divided by 1 times 10 to the power negative 2. So we can now write the force to be equal to 6.67 times 1 times 2 divided by 1, of course, and then you can have 10 to negative 11 times 10 to the power 4 times 10 to the power 2. So F can then be written as 13.34 times 10 to negative 5, or you can write 1.33 times 10 to negative 4 newtons. So you can see this is a very small force between the two objects because this is a gravitational force, so the force is very small. Let's look at the next example. Force on one mass due to two other masses. So in this case, I'm going to draw three masses on the corners of a right triangle like that, and I'll call this mass 1, that will be mass 2, and that will be mass 3. And the distance here is going to be R13. This is going to be R12, and we have forces between them. So what we want is to find the force on mass 1 due to masses M2 and M3. So let's do that next. So I'll redrawing this way. So this is M1, M2, and M3. So the force on 1 due to 3 is going to be this force. This is the force on 1 due to 3. And the force on 1 due to 2 is this force, like that. So both forces would tend to pull this object in this direction along the dotted line that I've shown there. I'm just showing the forces on 1 due to 2 and the force on 1 due to 3. So I'm leaving out the force on 2 due to 1 and the force on 3 due to 1. So by Newton's law of gravitation, the force on 1 due to 3 is given by G M1 M3 over R13 squared, and the force on 1 due to 2 is given by G M1 M2 over R12 squared. Then the net force on this mass M1 is just equal to, and first of all, let me do it in vector notation, is the force on 1 due to 3, vector notation, plus the force on 1 due to 2, and the magnitude of the net force on 1 is just the square root of the force of 1 on 3 squared, plus the force on 1 on 2, the force on 1 due to 2 squared. So I'll redraw those forces like that. So this is the force on 1 due to 3, and this is the force on 1 due to 2. And what we expect is, by parallelogram rule, to have a magnitude force Fn1, which is pointing in that direction, and we expect the angle phi to be this angle, which is the direction of the force on 1 due to those two forces. So we can say that the direction phi is equal to the tangent inverse of F13 divided by F12. So we've completed our example of the force on mass 1 due to two masses, mass 2 and mass 3. So this is like a recipe that you can use if you have this kind of arrangement that is shown. Okay, so I'll go to the next section, which is the gravitational force on an object that is falling close to the surface of the Earth. This is section 13.4. Suppose we have a mass that is falling close to the Earth. We can use Newton's law of gravitation to solve that problem. So let's go ahead and draw the diagram here. So let's say we have the Earth that way, and we have a mass falling close to the Earth. So this is the mass of an object falling close to the Earth. Let's say m subscript e is the mass of the Earth. So in this case, there's a force between the object and the Earth, and in return, the object pulls on the Earth also. So this is the force of Earth on object, and this is the force of object on Earth. And by Newton's law of gravitation, this is just equal to the gravitational force, like that, where r is the distance from here to here. So this is your distance r. So this distance will have a component h, which is just the height of that object to the surface of the Earth, and this portion will be the radius of the Earth, r subscript e. So we can say that r is equal to the height h plus the radius of the Earth e, and we shall use that later. In this exercise, since the object is falling close to the Earth, the only external force on the object is the weight of the object. We are ignoring air resistance. So we can say now that the weight of this object, mg, is equal to the gravitational force on it, which is equal to g, mass of Earth, mass of object, over r squared. You can cancel the mass of the object. So we can cancel out the masses, and then we'll be left with acceleration of gravity, g, equals gravitational constant, mass of the Earth, divided by r squared. And now let's replace r squared by our formula for r, which is the radius of the Earth plus the height, all squared. So this is acceleration of gravity, which we can use if you had an h involved. So suppose you're on the surface of the Earth at a certain height, h above the surface, above sea level. You can calculate acceleration of gravity at that height above sea level. And this will also apply if you are in a satellite orbiting the Earth. You can include the radius of the Earth and the height of the satellite in its orbit to calculate acceleration of gravity in that location. We can make a slight algebraic change to get g times mass of the Earth. We divide that by radius of the Earth squared, take that out, and then you add 1 plus h over radius of Earth and square it all that way. And so we will see then that gm of the Earth over the radius of the Earth squared is just a gravitational acceleration on the surface of the Earth, and divide that by 1 plus h over re all squared. So g at the surface is what we know as 9.8. So g at surface is 9.83 meters per second squared. So we'll leave that there and move on to the next section, which is Kepler's laws